In this video, I will explain the proof of Theorem 4 for the paper Uniqueness of DRS as the two-operator resolvent-splitting and Impossibility of three-operator resolvent-splitting. This is the statement of Theorem 4. The pair t, s, where the fixed point mapping T is a mapping from R2D to R2D, and the solution mapping S is a mapping from R2D to RD, defined by these equations, is a fixed point encoding. And furthermore, this fixed point encoding converges unconditionally for theta between 0 and 1 and alpha positive. Let's examine the equations. We write boldface z to denote the vector that contains z1 and z2, where z1 and z2 are both members of Rd, and we write boldface t to denote the mapping that contains t1 and t2, where t1 and t2 are both mappings that map R2d to Rd. The first line gives us the first resolvent evaluation. We take the first part of the input vector z and compute x1. The second line describes the second resolvent evaluation. We take the output x1, take the second part of the input vector z, add them, and evaluate the resolvent with respect to b to get x2. Then we form this linear combination with x1, x2, z1, z2, and perform the third resolvent evaluation with respect to c to get x3. Next, we compute the output of the fixed point mapping T and the output of the solution mapping S. To the best of my knowledge, this splitting does not reduce to an instance of any known splitting method. This is why we will prove Theorem 4 from first principles. Throughout the proof, we will write boldface y to denote the vector that contains y1 and y2, and boldface z to denote the vector that contains z1 and z2. Without loss of generality, let's assume alpha is equal to 1. As our first step, we will show that t, s is a fixed point encoding. We need to show two directions. For our first direction, assume z is a fixed point of t. Define a, b, and c in this manner. The definition involves the input z and the intermediate x vectors that we obtain while evaluating t, s. Add a, b, and c and use the fact that x1 equals x3 at a fixed point to get a plus b plus c equals 0. Since a, b, and c are defined so that a is an output of the operator a at x1, b is an output of the operator b at x2, and c is an output of the operator c at x3, the fact that a, b, and c sum to 0 proves that x1 equals x2 equals x3 is a solution of 3-op Rd. Let's now prove the other direction. Assume that x star is a solution to 3-op Rd. Let a, b, and c be the output of the operators a, b, and c at the solution x star, so that a plus b plus c is equal to 0. In other words, a, b, and c are the outputs of the operator that certify that x star is a solution. Define z star to be a vector of this form. Then it is straightforward to verify that z star is a fixed point and that the output of the solution mapping at the fixed point is x star. Next, let's show that t, s converges unconditionally for theta between 0 and 1. We do so by showing that t is non-expansive for theta equals 1 and appealing to the Km iteration theorem, which states that an average non-expansive iteration converges to a fixed point provided that a fixed point exists. Let theta equals 1. Define M to be the linear mapping from R2D to R2D of this form. This is the linear operator corresponding to the matrix vector multiplication by this matrix. Define the operator U in this manner. It is a matter of simple verification to check that the operator T can be expressed in this form where these symbols denote composition of operators from R2D to R2D. Define N to be this matrix. Now let's go through some algebra. Into this expression, we plug in the form of T expressed in terms of U, and we expand the squares to get this equal expression. Next, we use firm non-expansiveness of the resolvent with respect to C to bound this norm squared by this inner product. Next, we add these two expressions to get this expression. Let me explain the reasoning. Imagine we have this expression. Then we can equivalently write this in this form. And this is how we get the matrix N. Going back, this is how the matrix N appears, and this is why the sum of these two terms is equal to this term. The next step is to notice that this term is actually equal to 0. Imagine we have an expression of this form, where the two components on the vector to the right are equal. In this case, the matrix vector multiplication produces a 0, so the output is equal to 0. By this reasoning, the matrix M multiplied to this component is equal to 0, and that makes this component equal to 0. Let's further bound this expression. Remember that U was defined by this expression, We simply plug that in and expand to get this equivalent expression. Note that this giant norm is really a sum of two norms squared. The minus norm squared and the plus 2 norm squared add up to account for this term. The minus norm squared and the plus 2 norm squared add up to account for this term. This term is placed here, and this term is placed here. By firm non-expansiveness of the resolvent with respect to A, this term is negative, and we can remove that term and use an inequality. We use the firm non-expansive inequality to bound this term by this term. Therefore, this inequality is a result of using firm non-expansiveness of the resolvent with respect to A and the resolvent with respect to B. Next, we combine these two terms to get this term. We combine this term, and this term to get this giant minus squared, and this gives us this inequality. This completes the proof of Theorem 4.